Okay, so thank you very much for the invitation to this nice workshop. So indeed, today and tomorrow I will talk on Gromov-Witten theory of complete intersection, so the same topic as in Hülya's talk yesterday, and essentially I will cover the same material, but maybe more slowly and focusing on particular aspects. So today I plan to talk about the parts related to trading insertion of primitive cohomology classes for nodes and explaining the related representation theory. And tomorrow I will talk about relative Gromov-Witten theory and foundational aspects of nodal relative Gromov-Witten theory. So today I will talk about things related to nodes and representation theory. So it will be some relatively classical and elementary representation theory, but still it's a nice story that I plan to describe. Okay, so what we're talking about is Gromov-Witten theory. So we fix X, some smooth projective variety over the field of complex numbers. And then Gromov-Witten theory is based on Modi spaces of stable maps. So I have Modi spaces M, G, and beta of X, which are Modi spaces of stable maps, so maps from nodal curves, arithmetic G with n smooth mark points to X of class beta, and so which are stable. And you can think about these Modi spaces as defining correspondences between, on the one hand, n product of X, where this morphism is evaluation as the n mark points. And on the other hand, the Modi space of stable curves. So if you have a stable map, you can just remember the domain curve. It's not necessarily a stable curve, but you can always stabilize it to produce a stable curve. So you get a morphism from the Modi space of stable map to the Modi space of stable curves. And then on this Modi space of stable maps, you have some particular cycle, the virtual fundamental class. And you can use it through this diagram to start with cohomology classes here and produce cohomology classes here. So you get a map from, if you have n cohomology classes, you will get a map to cohomology of Mgn bar. So if you have n classes alpha 1, alpha n. So let me call evaluation at the highest mark points here, and let me call pi this projection here. Then you can just pull back the cohomology classes by the evaluation morphism, cap with this virtual fundamental class. And then push forward to the Modi space of curve. Okay, and so the classes you obtain like that are so-called Gromov-Witten classes. So in the case where these cohomology classes are top dimensional, or if the associated homology classes are zero dimensional, then simply taking the degree of these zero-dimensional cycles produce Gromov-Witten invariants. It is a case where you expect to have finitely many curves and you kind of count them. But more generally, you can have families of curves, and this thing as the classes inside the Modi space of curves defined by precisely the curve which can be realized by such a stable map. And then we have these general questions like, of course, either computing or what can we say about these classes. And so inside the cohomology of the Maudit space of curves, you have the tautological ring. Let me say tautological subring. Inside the cohomology ring of the Maudit space of curves. So I will not recall the definition, which was in Hülya's talk yesterday. It's a nice subring. And so the general question that you can ask is, when are Gromov-Witten classes tautological? And there is some obvious obstruction for that. So obvious obstruction is the fact that these tautological rings that I did not recall the definition, actually it is made of cohomology classes which are always classes of algebraic cycles. So this thing is and so in particular, of Hodge type PP, so in the Hodge decomposition of this cohomology group, in the HPQ decomposition, all the elements here live in the middle part PP, and so even more specially in even degree. And why is it an obvious obstruction? Because the classes we start here, the cohomology classes on X, is F has some interesting odd cohomology, odd degree cohomology, or if it has interesting cohomology which are not of Hodge type PP, then there is no general reason why these Gromov-Witten classes should be of this form. But what we'll see is that in the special case of complete intersection in a projective space, so typically these varieties can have interesting cohomology in odd degree or have a non-trivial Hodge theory. But even in this case, we'll see that in this case, actually Gromov-Witten classes are tautological.
So it appears that's algebraic because things depend on parameters, sections. And class should be invariant under the same in the whole family. It's kind of a priori clear that classes will be algebraic cycles as computer. By pure arithmetic reasons, because you have Hodge structure depending on parameters, but the result doesn't depend by invariance.
Yeah, so essentially what we'll discuss will be essentially deformation variance, which indeed is a key point. And so in this special case, this obstruction is not there, and actually it will be tautological. Yes.
Yeah, also just want to make a comment that
yes.
With this reasons actually Malin proposed in the very early days of this Gromov-Witten invariance to study Gromov-Witten invariance of spaces MJ and bar themselves, because they already have this interesting structures.
Yeah, so you
themselves.
I see. Okay, so we start recalling very basic things about cohomology of complete intersections, because they're the thing which enter here. So I consider X some m-dimensional complete intersection inside projective space of dimension m plus r. So complete intersection. And then by the Lefschetz hyperplane theorem, so we know there's a natural map from cohomology of the ambient projective space to the cohomology of X is an isomorphism for every I between 0 and the top degree, except in the middle degree m. And as a part of the theorem, in the middle degree part, this cohomology of the projective space will embed inside the middle degree cohomology of X. Maybe I will choose. Okay, so let me just distinguish the two cases. So if m is odd, then obviously the part coming from the projective space is 0. So in this case, this middle degree cohomology is the full thing is primitive. The primitive cohomology, and on this middle part there is an intersection form. So I don't know, in the differential form language, something like that. So geometrically, just intersection of middle dimensional cycles. And if it's if m is odd, this thing is a non-degenerate skew symmetric form. And if m is even, then this middle degree cohomology has a one-dimensional piece coming from the ambient projective space. Let's say I work with skew coefficients. And then there is some orthogonal part, which would be the primitive cohomology. And here is orthogonal with respect to the, again, the intersection form, which now is non-degenerate symmetric bilinear form. And actually, the restriction to the primitive part is still non-degenerate symmetric. So from now on, I will denote by V in a uniform way the primitive part of the cohomology. Let's say with complex coefficient, and I've used this vector space with this non-degenerate bilinear form, which is either skew symmetric or symmetric depending on the parity of M. And so in particular, you have the corresponding orthogonal group and a symplectic group. And now we'll come to the first key point, which was already mentioned, which is this thing move in families that depend on some parameter. So there will be a monodromy monodromy. Okay, so for such a complete intersection, we have some space of parameters. So which are just our equations. So the element inside projectivization of space of degree d(ith) polynomial if my x is of degree d1 to dr. So this thing is a space of parameters for the equations. And I want my complete intersection to be smooth. So inside it, I have some open set which parameterize a smooth complete intersection. So this thing is a complement of some discriminant hypersurface inside this space of parameter. And then you get an action of the fundamental group of this space. So you get monodromy representation so from the fundamental group of this space, let's say some base point Q acting by linear transformation on the cohomology of the corresponding complete intersection. And the part coming from the ambient projective space is fixed under this monodromy action because the ambient thing is fixed. So actually the action factors through the primitive part of the cohomology, so what I call, let's say, GLV. And of course, this monodromy preserves the intersection pairing, which is something topological. So actually, this thing mapped to the orthogonal or symplectic group, depending on the priority of M. And now we can introduce some kind of algebraic monodromy group. So the G, which will be the Zariski closure of the image of the fundamental group. Okay, so it's an algebraic subgroup inside the orthogonal or the symplectic group. And then there is a general result that Hülya already mentioned yesterday, it's the result of Deligne. We say that in most cases, the monodromy is as big as possible. I mean, G is equal to the full orthogonal or the full symplectic group. So outside exceptional cases, and so today I will forget about exceptional cases. So for now, and I will just assume that this thing is true. We consider the case where the monodromy is as big as possible. And so why is this monodromy? Why is the fact that this monodromy is big useful? Is because, as mentioned, Gromov-Witten invariants are deformation invariants. So this monodromy will give constraints on Gromov-Witten invariants or Gromov-Witten classes. So assume that I'm looking at some Gromov-Witten invariant or some Gromov-Witten classes in some genus, some number of mark points, some curve class. So I draw some kind of genus G curve, and I have various mark points. And at these various mark points, I insert various kind of cohomology classes. And I have two kind of cohomology classes, the one coming from the ambient projective space and the one coming from the primitive cohomology. So let me fix insertions coming from the projective space at some number of points. And actually, in this story, I also want to allow psi classes insertions. So I also fix psi classes insertions. So I fix some integer for every mark point, which tell me which power of the psi class do I insert. So, and I view the result as a function of the primitive insertions. And then we assume there is some number of mark points at which I insert things coming from projective space, some other number where I insert primitive things, let's say n of them, and then I just get some map from V tensor n, I mean just the n primitive things that I insert to either complex numbers, if I look to Gromov-Witten invariants, or cohomology of mgn bar, if I look to Gromov-Witten classes. And just for notation, I would just call GW this particular object.
Do you also allow psi classes in this primitive insertion?
Yes. So here psi classes at all possible points. So both the one coming from projective space and primitives. And somehow, so the powers of psi class, they are fixed, and the only thing I vary are the primitive insertions. And maybe just for notational purposes, it does not really matter actually, but I would just pretend that we're looking to numbers, let's say. So that, and then I can think to C thing as if simply be an element of the dual, just an element in this particular vector space. And so the question of computing these Gromov-Witten invariants or Gromov-Witten class is just computing this particular element inside this particular vector space. Another point is that on this vector space V, we have the action of the monodromy. So we have this monodromy G acting on V, and actually now that I'm assuming that we're in this big monodromy, it's a full orthogonal or full symplectic group. And now what deformation invariance of Gromov-Witten theory tells me is that these particular elements in this vector space live in the invariant part. Maybe I wrote G. Okay, so G acts on V, it acts on the tensor powers of V. So it acts on the space of multilinear forms on V. And deformation invariance of Gromov-Witten invariants implies that these particular elements live in the invariant part. Okay, so it's really saying that, yes.
You can finish the sentence before.
No, sure, no.
So as you go along, for me, it would be helpful to visualize or try to visualize the simplest non-trivial example. So I was wondering if, for example, does this story sort of collapse to something silly when one? So like you're in P, like you have, I guess, the middle cohomology is like curves in P2.
So which examples did you say?
I'm wondering if, does everything become too simple when you're looking at things in complete intersections within P2?
No, so already maybe I would try. Sorry. Yeah, so some of the first non-trivial class of example is, as in Hülya's talk yesterday, simply just a cubic in P2, an elliptic curve. Then you can already run this story. So in this case, the primitive cohomology is just the first degree cohomology of the elliptic curve. So it's okay, so and then you have the monodromy action, which in this case so will be the symplectic group, but in dimension 2 it is the same thing as SL. So if you want, you have G equal like SL2 acting on this two-dimensional cohomology, and the claim is that so these Gromov-Witten invariants or classes, they are like multilinear form on this two-dimensional vector space, and they live in the SL2 invariant part.
Is it obvious why the action extends to the Zariski closure?
I think it should be. I think it is, yes. you can, yeah.
Can you say again, especially in this example, what it means when you say insertions on the n+1?
Sorry?
Up there you said fixed insertions.
Yes.
Can you say again what that means maybe in this example?
Yeah, so in this example, the thing coming from the ambient projective space are just the degree 0 part of the cohomology and the degree 2 part of the cohomology. So this thing is just so this thing is just generated by 1, and this thing generated by something you can call the class of a point. So you study maps from some genus G curves to your elliptic curve with some number of mark points. And at some of these mark points, you insert this class 1, at some other you insert this class P. But at some other, you insert these primitive classes A and B, which generate this first degree. And which geometrically are just one cycles on your elliptic curve.
So Pierrick, you crossed out the target H star of MGN bar.
Yeah, but
you're just not looking at it. It's also supposed to be invariant of the primitive.
Yeah, that's right. You view that as like some ring of coefficients, and it's still true.
Okay.
Okay, so this thing is geometrically clear. You have your complete intersection. You move the coefficients. You have some parameter family of varieties, and you count curve in this variety and satisfying some constraints. And then you move your parameters around. You deform your constraints. So locally, they are cohomology classes, so they locally deform trivially. But then globally, when you come back, they can come back to some different classes. It is a monodromy action. But the claim is that the curve count does not change. Okay, so concretely, if you have some element G in this monodromy group G, and if I look to these Gromov-Witten classes evaluated on cohomology classes G applied to alpha 1, times G applied to alpha n, then this thing is equal to the Gromov-Witten theory of alpha 1 times alpha n. And of course, the fact that the monodromy is big is good in the sense that its constraints strongly these Gromov-Witten multilinear forms, so these Gromov-Witten invariants, or these Gromov-Witten classes. So now Gromov-Witten is inside the invariant part, and so now we can start using some very basic invariant theory. So, as it was already mentioned yesterday by Hülya, first of all, minus identity is inside the orthogonal or symplectic group. So automatically it implies that this Gromov-Witten invariant is 0 if n is odd. Because if you can just flip the sign of all the alpha I, you have a global sign which is -1 to the n, and so you get this vanishing. So from now on, assume that n is even, and I would just change notation and replace n by 2n. And so now to simplify, I will assume that m is even, so that we're in the orthogonal case. So the symplectic case will be exactly the same, except there are extra signs to keep track of, and I will not go to do that now. So from now on, I assume that m is an orthogonal case. So now you have some very classical kind of question. You have a vector space V with a symmetric bilinear non-degenerate form. You have the orthogonal group. You consider 2n tensor powers of V, maybe dual. And you ask what is the space of invariant? What is the space of orthogonal invariant tensors? And so there is so it's a very classical story. It goes at least back to Weil. And so the first part of the answer is that it's easy to produce generators. So easy to produce generators. And so the generators are indexed by n pairings. So I will fix P. Some n pairings, so it's a way to form n pairs from 2n elements. And as yesterday, we represent n pairing by the arc diagram. So for example, if n equals 2, so 2n equals 4, you are looking to ways to produce 2 pairs out of 4 objects. And there is 3 ways to do that. You can pair 1 with 2 and 3 and 4, or you can pair 1 with 3 and 2 with 4, or you can pair 1 with 4 and 2 with 3. And if you have such a pairing P, then you can write down some invariant tensor. So ideal by alpha P, which goes from V tensor 2n to C, which simply takes some tensor Vi and map it to the product over the pair inside the pairing. And for each pair, so for two indices I and j, which are paired by the pairing, I look to the corresponding vectors Vi and Bj, and I pair them by the bilinear form. So this thing is clearly a linear map from V tensor 2n to C, and it's obviously G invariant because this thing is a bilinear form which is invariant under the group. And then the so-called usually first fundamental theorem of invariance theory tells you that some of this thing generates the space of invariance linearly. So you have a map from what I would call C Pn. So this thing is just a vector space with a basis given by n pairings. Maybe I wrote like that. Direct sum over P n pairing C times some basis element. So this thing is a vector space of dimension equal to the number of n pairings, which is 2n minus 1 double factorial. And this thing just constructs a map from this space of n pairings to the space of invariant tensors. And the content of the first theorem is that this map is surjective. And let me call phi this map. Okay, so if our goal is to understand our Gromov-Witten invariant of our Gromov-Witten class, which is an element inside this space, and we know that it is in the invariant part, and if we want to describe it in a kind of concrete way, then it's a good first step because you have kind of explicit generators of this space. So the thing we are looking for will be some linear combination of these invariant tensors. The only problem with this description is that in general there is a kernel. There is some relation between these tensors. And so to say something more precise, we need to describe this kernel. So yeah, so the question is, what is a kernel? So you can show that if the dimension of V is big enough with respect to n, actually there is no relation, since this thing is just some isomorphism. But for general V, there will be a kernel, and the question is how to describe it. And so here there is a nice story involving, so one way to describe it is a nice story involving representation theory of the symmetric groups. Yeah, so because we have a space of pairings, and there is an obvious action of the symmetric group with 2n elements on the set of n pairings. Simply you permute in this picture here, you just permute the labels 1, 2, 3, 4. So you get an action of this symmetric group on the set of pairing. And so you get a representation of the symmetric group on the vector space generated by the pairing. And so each time you have a representation, the most basic question is, what are the pieces when you decompose it into irreducible representations? So here I recall that irreducible representations of the symmetric group, so here it's on 2n letters, there are a natural one-to-one correspondence with partitions of 2n. So partition of 2n is one way to write 2n as lambda 1 plus lambda l, let's say. And let's say I choose so a partition of some integer into positive integers. And as usual, I can represent this partition by the corresponding Young diagram. So I will view lambda, some partition, as being the Young diagram with L rows and with lambda 1 boxes in the first row, dot lambda L boxes in the else row. And maybe there is always some kind of ambiguity, so here I will use, just so that the statement would be correct, I'm choosing this correspondence such that the trivial representation, so in this correspondence I choose the one such that the trivial correspondence corresponds to the trivial partition 2n equal 2n, which in this correspondence correspond to the Young diagrams made of a single rows and 2n boxes. And the sign representation correspond to the partition of 2n into sum of 1s. So the corresponding Young diagrams consist of a single columns made of 2n boxes. Okay, and maybe let me just call m lambda the irreducible representation corresponding to the partition lambda. Okay, so this thing is a review of irreducible representation of a symmetric group. Now you have an explicit representation given by action on pairings, and so you can ask what are the irreducible representations which appear when you decompose into irreducibles. And the fact is that the answer is very simple, which is this space of pairings as a representation of a symmetric group is a direct sum over lambda partition of n of 2n. And the ones which appear are the ones which have even rows. So let me say with rows of even lengths. So for example, if n equal 2, this theorem tells me that this space of pairing decomposes into, so for n equal 2, 2n is 4. So I'm looking to all the partitions of 4, but only the ones which have even parts. Okay, so I have 4 equal 4, which correspond to this 1. And then I have 4 equal 2 plus 2, which correspond to this 1. And so the space of two pairings is a 3-dimensional, so this thing has dimension 3, corresponding to the 3 pairings which were drawn at some point. And this thing is dimension 1. It is a trivial representation. And this thing has a dimension 2. And you can check that if I denote x, y, z, the coordinates with respect to the natural basis given by the 3 pairings, then this thing is a line x equal y equals z, and this thing is a plane x plus y plus z equal to 0. Okay, now finally, so what is the point of that is that it's useful to describe the kernel of this map phi in terms of these decompositions. So what is usually called the second theorem of invariance theory. It describes the kernel of phi. So it is a subspace from here, and it is made of the pieces m lambda. So where lambda is a partition of 2n, it has, I would just say, even rows, so rows of even length. And now the condition which defines the kernel is that the length of the partition lambda should be at least dimension of v plus 1. So this thing is the length, so it's the number of parts. Okay, so depending on what is the dimension of v, this thing tells you exactly what is a kernel. So in particular, if you just kill the kernel, so if you just if you consider phi but restricted to the complement direct sum, if you consider the map from partition with opposite inequality, then this thing is invariant to your space of invariance. And so you have some extremely concrete description of the space of invariance in terms of this decomposition. And in particular, in our stories, our Gromov-Witten invariants, which we are leaving here, if you want, you can write it explicitly as an element inside this space. Okay, so now we'll finish by doing finally some geometry. Until now there is no geometry, there is just deformation invariance and say, okay, it sits in some space, which can be described using a deformation theory. And the geometry part involves replacing these primitive insertions by nodes. Yeah, sure. Sorry. Okay, so nodal. So I will not review now the discussion which was in Hülya's talk yesterday, which was to compute these numbers. We like to use some degeneration argument, but because of vanishing cycles, we cannot directly apply degeneration arguments to these invariants containing primitive cohomology classes. And so the idea is to replace these invariants with primitive cohomology classes by so-called nodal invariants without insertion of primitive cohomology classes. And so what are these things? They are just a variant of Gromov-Witten invariants where you, let me just say, impose nodes in the domain curve. So the most general kind of invariants like that, they are indexed by graphs. So if you fix gamma some, let's say, pre-stable graph, so just some finite graph with some number of vertices, edges, and let's say the vertices are decorated by various genus, then inside the moduli space of all pre-stable curves, so let me denote by MGN, moduli space of all pre-stable curves, so like all nodal curves with mark points, with n smooth mark points. Inside that there is some kind of stratum of curves, which is essentially the closure of the locus of curve whose dual graph is given by the graph gamma. Okay, so this thing is stratum. So if you want, it is a set of pre-stable curves. So meaning they have components corresponding to vertices, and they have nodes corresponding to edges. And maybe I also have legs corresponding to mark points. And I take the closure. And so essentially my nodal Gromov-Witten invariants are defined by imposing my domain curve to be a nodal curve of this type with dual graph retract onto this graph gamma. So in other words, a curve, if I draw this picture, a curve, if I look to Gromov-Witten theory to nodal Gromov-Witten invariants indexed by this graph gamma, then I'm looking to curve which is made of some curve corresponding to this vertex, 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 and then I have various nodes gluing the various components corresponding to the various edges, and I can also have self-intersecting node corresponding to the loops. Okay, so usually, so you can define Gromov-Witten for every choice gamma of such a stable graph. You can define Gromov-Witten invariants. So you impose your nodal curve to have a pattern of nodes prescribed by the graph gamma. And usually, it's not extra information with respect to usual Gromov-Witten invariants, because there is a so-called splitting formula in Gromov-Witten theory which just allows you to remove a node by opening it. So, example, let me just consider some Gromov-Witten invariants where your graph gamma consists of a single loop, so some number of legs corresponding to mark points. So I'm just looking to curve where I impose to have a non-separating nodes.
So when you're defining Gromov-Witten invariants, you want to compactify this six, right?
Yeah, so here I put this bar, which means like closure. So obviously the curve can degenerate further inside each of the vertices. So yes. And so if I have such Gromov-Witten invariants, so I have various mark points, I have various insertions. And if I want to compute these Gromov-Witten invariants, it is actually the same thing as computing curve without nodes. But where I have opened the node, and when I open the node, I've created two mark points. And geometrically, if you want this count of curves to be the same as this count of curves, the only thing you need to impose is that these 2 points, by the map to x, they should map to the same point. Right? Because this point maps somewhere in x, and these 2 new points, they should map to the same point so that we have an equality of count. And so imposing that means that at this point you should insert the class of the diagonal in the cohomology of x tensor cohomology of x, where delta is like x inside x plus x is diagonal.
In general, there's some issue with this, right? When you have loop chains of genus 0 curves, does this go away here?
Yeah, that's right. So the statement of the splitting axiom or splitting property of Gromov-Witten theory is that this statement is true for Gromov-Witten classes. And so Yes, because intuitively, it's virtually like the classes only see like top dimensional thing, and this kind of phenomenon is like lower dimensions. But if you do things like quantum K-series, and you see this kind of lower dimensional thing. And now the main statement I want to state, which is in our paper, is that if I want to determine my Gromov, so now I come back to my story of Gromov-Witten invariants as a function of some numbers 2n primitive insertions. And I can just, so this thing was a linear map from V tensor 2n to C. And what I can do is to evaluate it on some diagonal class elements, and it will produce me nodal Gromov-Witten invariants. So for every P and pairing, I will define nodal Gromov-Witten invariants attached to this pairing P. So here we're counting curves with 2n insertion of primitive elements, let's say 1 to 2n, and also various psi classes at the various points. And here for a fixed choice of pairing P, it gives you a way to form n pairs out of these 2n points, and for each pair of points, you glue them together to create a node. So you obtain a curve, you obtain a nodal curve with 2n non-separating nodes. And here, remember, I also had psi classes at the points, so I still insert psi classes along the branches of the node. And I look to this particular Gromov-Witten invariant. So for every pairing P, I can look to this nodal Gromov-Witten invariant problem where now there is no longer primitive insertion. So now this thing is just a number. For every pairing P, I get a number. And the claim of this theorem is that if you know all of these numbers for all possible pairings, then you can recover this linear form on the primitive cohomology. And the reason for that is by the splitting axiom, by the splitting property, these nodal Gromov-Witten invariants, actually it is equal to these Gromov-Witten invariants, but evaluated on diagonal classes. So evaluated on, let me write over the product of the pairs inside the pairing of delta ij, where delta ij is a diagonal in the place I and j. So here, let me skip some details. In general, the diagonal inside, there is a full cohomology of X, but I only care about the parts which come from the primitive part of the cohomology. The other part is made of things coming from the projective space, so I can forget about it. Okay, so definitely all these numbers knows a lot about this invariant form. It knows this invariant form evaluated on all these tensors. And so the statement of the theorem is that if you know all these numbers, you can recover this form.
It's just a corollary of first.
Yeah, so I think yesterday you were making some comment about invariance, co-invariance. So I think it's true. So if you just want to prove this theorem, indeed it follows from abstract reasoning directly. So maybe I would just end by this comment, and because I have the luxury to have a talk tomorrow, I will continue tomorrow the following thing. So I will just end by this comment. So very generally, if you just have a G group, let's say acting on some space, I don't know, let me call W. And if you look, so you have a space of invariance. And so dually, if you look, let's say finite dimensional representations, if you take the dual, you have a map from the dual space to the dual of the invariance. And inside the dual, you have the invariance of the dual. So you have invariance of the dual like that. So you always have a map from the invariance of the dual to the dual of the invariant. And if G, so here the point is that G is reductive, it has a semi-simple representation theory, everything is decomposed into direct sums. And so this thing just implies that this thing is an isomorphism. So said differently, the natural pairing from invariance, so the natural pairing from W to W dual to C, if I view it at the level of invariance, is still non-degenerate. And so here what I care about is an element in a space of invariant. And here the only thing I need to know is that by the first theorem of invariant theory, these diagonals generate the invariance of the dual. So some of these delta ij, they kind of generate C space. So, and because this thing is not degenerate, if I know this thing evaluated on all these elements, I can recover this thing. So just from this kind of abstract reasoning about invariance of a projective group, you get what we want. But actually, tomorrow I will describe some of the explicit form of this reconstruction by writing down some kind of explicit matrix going from this number to this number and discuss the properties of this matrix. And I will stop there for today.
Okay, does anybody have any questions for Pierrick?
Yeah, the very beginning of your talk,
Yes.
I was wondering, so this question about whether Gromov-Witten classes are tautological.
Yes.
Is that known for curves? Like when the target is a curve?
Yeah, so it was known. And yes, and actually the story I will describe will give a slightly different proof of that. So actually for curves, some of the elliptic curve is the only really difficult one because you can always break a genus G curves to elliptic curve without any vanishing cycles. And then for elliptic curve, you can run this story. But it was known before, but for slightly, with essentially the same kind of arguments.
Not without any vanishing cycle, without non-separating cycles. There will be vanishing cycles, they won't be elements of H1, they will be in the fundamental group.
That's true. Yeah, any like cohomological vanishing cycles, yes. Exactly.
Okay, if there's no more questions, then thank Pierrick again.